Newton's second law of motion allows us to look into the future and predict the position and velocity of a system. Given the net force, the final velocity, the object's mass, and its initial position, we can predict the object's position at any given time in the future. In this lab, I observed the motion of a AA battery rolling at a constant speed in one direction. I captured a video of the battery's motion and analyzed it on tracker to extract the object's time and position. This information was then used to calculate the object's initial velocity and initial position to create a computational model. By plotting both my observed positions versus time and the predicted position versus time, I was able to compare both sets of data and determine that model represented the observed data well. I began by capturing the video and editing it in Tracker. For this experiment, I labeled the positive y-axis pointing up and the positive x-axis pointing to the right. I then selected the parameters of the video to include only the footage of the battery moving at a constant velocity. The initial position of the object was selected to be the center of the battery in the first frame of the edited video. The initial position of the ball is also where I selected to be the origin of the axis. I went through the video frame by frame, selecting the center of the battery each time to generate position versus time points. I calculated the initial velocity of the battery using these points, which allowed me to create a computational model using Python. In this model, I set the net force equal to the zero vector. The importance of this can be seen in Newton's second law, which shows that the final velocity is equal to initial velocity plus the net force divided by mass multiplied by the change in time. If net force equals 0, then the mass and time change do not affect the velocity of the ball, which means final velocity equals initial velocity. If this is the case, there is no difference in the velocities, which means acceleration is 0 and the object is moving with a constant motion. In the model, the system moves at a constant velocity, which is ideally what the observed data should show as well. This computational model records the position for each time t in the graph until the time reaches the last recorded time of the observed data. These calculations are based on Newton's second law of motion. The law can be represented by the equation final position equals initial position plus average velocity multiplied by the change in time. The code calculates the final velocity and then uses this velocity as the average velocity for this equation, which calculates the new position. Each position and time is recorded into a spreadsheet. This process is continued until the indicated time is reached. Next, the times and positions of both the predicted data and the observed data are used to generate a graph that compares the two. While examining the graph, we can see that the two lines do not match perfectly. The model predicts that the battery should have ended up 0.167 meters away from its initial position. However, the observed data shows the battery ended up only 0.131 meters away from its initial position. This 0.036 meter difference suggests that there may have been some uncalculated forces acting on the object. I did not take into account the friction that the battery could have had with the table, which could have caused the velocity to decrease. Another unaccounted for force is the air resistance, which would also have resulted in the slowing of the battery. Besides unaccounted for forces, another cause for the differences in the results may be human errors. The information collected for the observed data relied on my selecting the center of the object at each frame in the videos. If I was not precise and accurate in my selecting points, the data would have been inaccurate. This could also account for the differences in the results. When you analyzed your video data in Tracker, you made a choice of the orientation of the axes. Discuss briefly how your results would change and how they would remain the same if you were to flip the axes. If I were to flip my axes, all of the position points would have been negative. When I calculated the initial velocity, it would have been negative as well. This would cause the object in the computational model to move to the left instead of to the right. Other than the positions and velocities being negative, nothing else would change because the negative sign merely indicates direction. The magnitude of all my results would remain unchanged. Your observations can be predicted well by your computational model when you set the net force equal to 0. Is it possible for you to say how many pushes and pulls are added together to give the net force 0? There are a myriad of forces that could be present. However, as long as they balance out to equal 0, the results will remain unchanged. In my results, there were some differences. Whether they were the results of unknown forces or human error, I do not know. However, it was probably a combination of the two. I do know that because my system was rolling on the table, friction was present, as well as drag. Based on the comparisons of the predicted data and the observed data, I was able to conclude that Newton's second law represented constant motion well. Because we do not live in a vacuum, there are outside forces acting on the battery. If the forces had added up to equal a net force of 0, they would not have affected the data. However, this was not the case, and it was reflected in the graph, as well as the discrepancies from human error. Despite some errors in the results, Newton's second law is an accurate representation of an object moving in one direction at a constant velocity.